Hey guys, we're going to be talking about electric current. This is the end. Isn't that nice? So basically circuits and charges moving through wires. So in my opinion, this is why we live the way we do. This is why we have the quality of life that we do. Because at any point you can flip a switch and turn things on. You can go downstairs in the middle of the night and make a sandwich and everything's going to be running. So we're going to be talking about this. Make this bigger real fast. So these are the three things you need in any electric circuit: voltage, current, and resistance. And the way I think about it, voltage is like the push. It's like a pump for electric charges. If you have a very tall building, how do you get water up to the very top? You have to pump it up there, right? And so that's kind of the way I see voltage. It's like the push. It's a pump. Current is the actual electric charges moving. So technically current is electrons. And they're moving from the negative part to the positive part of your battery. That's not the way we actually do problems. We actually do problems the other way. We do problems thinking like positive charges going from the positive plate over to the negative plate, because Ben Franklin did it like that, and we're still doing it like that. So we actually talk about positive charges moving when we do all these problems, but that's really not what's happening. It doesn't really matter. Okay? Current is moving electric charges. So I always think about current like water flowing through pipes. That's my current. Finally, resistance. This is like friction, or if you have constrictions in your pipe, then that's what resistance is. These three things are typically governed by this equation right here. This is called Ohm's law. Got to write that down. Way over there. That's Ohm's law, which is neither a law nor was it first discovered by Ohm, but there it is. That's the relationship between those three. A lot of people don't write it like that. They write it V equals IR. So that's a thing. But these are the three things you need in any electrical circuit. And yeah. Okay. So this, which you see on the screen, is called a series circuit. Series circuits are very simple. The best thing about a series circuit is that it is simple. You don't need a lot of stuff. And so things like remotes for things are usually wired in series. Christmas lights used to be wired in series. Not so much anymore. But this is your series circuit. These little blue dots are representing charges that are moving through the circuit. And they're actually doing it the right way. They're little negative charges, and they're moving from the negative plate to the positive plate, which is usually not the way we draw things, but that's really what's going on. And then you have some bulbs. And these are called, really a bulb is called a resistor. Resistors look something like this. And anything you plug into your circuit is actually a resistor. If you think about cooking pasta on your stove, if some of you have electric stoves like I do, all that is a resistor, and all it does is resist, and it gets hot and it slows charge down, and so that's a thing. So anything you plug into your circuit is a resistor. So we have three bulbs here. Now here's the deal: if I take a bulb out, then the whole thing stops. So the problem with series circuits is that if one part fails, then everything quits. That's a thing. Put a bulb back in here. Uh-oh. Crazy. There we go. So notice the speed at which these little suckers move. They're not moving very fast. And the thing about this is, let's say if I plug in another bulb, then what will happen? Another bulb here. Oh my gosh. Then they're not as bright. I don't know if you notice. You might have to back the video up a little bit, but now the bulbs are all not as bright, and they're not moving very fast. These little electrons aren't moving very fast. So the more stuff you plug into series, the slower things move. Let's compare this with a parallel circuit. So here's a simple parallel circuit. I've only got one voltage source, just like in my series circuit. In my parallel circuit, though, you see that all of the electrons are moving very fast, and all these bulbs are nice and bright. And this is the great thing about these circuits is that, and this is creepy, but no matter how many of these things I plug in, all of the bulbs are still going to be nice and bright. I'll show you. We'll plug in another bulb here. And it should be just as bright as all the others. See? They're all still nice and bright, and all these little things are moving really, really fast. Now the cool thing about... Alright guys, another thing we need to talk about is resistance. Resistance is its own big topic here. There's an equation for resistance just by itself. Rho, it's called rho, divided by length times length over area. Rho is a constant. This sucker is a constant, which will probably be given to you unless you're trying to solve for it. But most of the time you're not trying to solve for that. L is the length of your wire, and A is the cross-sectional area of your wire. Wires are usually, if you take a wire and chop it and look at it, a wire is a circle. So A down here is usually pi r squared, because it's a circle. This equation will tell you what happens when, how much resistance you get when your wires are longer or shorter or bigger or smaller or whatever. So because R and L are both in the top of their respective fractions, this R is really R divided by 1, right? Since they're both in the top of their respective fractions, then if the length of your wire gets bigger, resistance will get bigger. So long wires are going to have a lot of resistance. Cross-sectional area is in the bottom of the fraction. So if cross-sectional area gets bigger, resistance will get smaller. Those two will be inversely related. So if you have really gigantic thick wires, there's not as much resistance. You can get more, stuff moving through. Like if it's a water pipe, you have more water able to move through. Maybe not quite as much resistance. So this is a good thing just to understand this. This equation would be good. Kind of forgot about current. There's an equation for current. This is it. Current is I, which I've never liked, but it is. I is Q over T. And Q are, if you remember, we talked about electrostatics. In static electricity, Q is charges. So Q is the number of charges moving in a particular time, and we call that current. Current is measured in amperes, and most people shorten that up just to amps. 1 amp of current is more than enough to fry someone. 1 amp of current is actually a lot of current. So you usually only need about half an amp or even less. I used to be bad, and I used to say things like, it's not the voltage that kills you, it's the amps. But, I was wrong about that way back when. It turns out that voltage can kill as well. But anyway, usually current is the thing you got to watch out for. And you only need about half an amp in order for it to get you. The charge on an electron is known. So that's the charge of a single electron. 1.6 e negative 19, and actually it's negative 1.6 since it's an electron. If you have a proton, then it's positive 1.6 e negative 19, right? Usually when we're talking about current, we're talking about electrons moving. So let me just get rid of that proton real fast. So that's the charge per electron. And if you take that number and type it into your calculator, and then you find the reciprocal, you get, so the reciprocal for that 6.2 e, I always forget what this is, 6.25 e to the 18. which is a really big number. See, what's going on here is this is charge per electron. The reciprocal, right? So this is charge per electron. This, when you flip this, you get electrons per charge, or number of electrons moving per charge. So it's the reciprocal, right? And this tells you the number of charges moving past a point in a wire in 1 second. And that's what we call 1 amp. So 1 amp is more than enough to fry someone because, I mean, look at the size of that number. That is a lot of charges, and your body is very electrical. And so if you get all that charge, you know, it's just going to stop things. Which is why if you try to resuscitate someone, if you take those little paddles and put them on them and you try to shock them and their heart is beating, you can stop their heart, right? Because you're shocking them with, you know, electricity. So anyway, this number is going to come in handy. You might see this one as well.